we are very delighted to have Dimitri van Ville with us today to give us a talk on the title Fractals in Your Brain, Scale-Free Temporal Organization of EEG Microstates. So Dimitri is a professor at the University of Geneva in the Faculty of Medicine, Department of Radiology, and the EPFL, School of Engineering Institute of Bioengineering. He has done a huge amount of service, bunch of editor positions in various journals and so on, and his research interests include wavelets, sparsity, pattern recognition, and the applications in biomedical imaging such as fMRI, EEG, and so on. So without further ado, Dimitri, over to you. Thanks.
Thank you very much, Faisal. I would like to thank you and Steve for this excellent organization. It has been really a pleasure to be here in Vancouver. And I especially like Vancouver because it gives me the opportunity to meet some friends who work over here. So it's always very nice to come back. So I hope I will keep up because I have the jet lag a little bit working, and now it's 2 a.m. in Europe. So it's and this talk is like about resting state, so it's dangerous as a combination. But I try to keep up. So the title of today is about fractals in your brain, more specifically temporal fractals. And so we will see whether there is some scale-free temporal organization as we can measure with EEG. And so this is joint work together with Julian Britz and Christophe Michel from the EEG lab at the University of Geneva. And it has been a lot of fun to work on this topic with them. Now, especially for the people who are not following the field of neuroimaging very closely, I would like to start with this slide, which I try to convey that there is a particular interest now since about 10 years in studying the brain at rest. And so traditionally, we have always looked at evoked activity. So we had a certain stimulation paradigm, and then we did imaging, and we were looking for evidence of how, in the signals that we measure, of whether there is something going on related to the stimulus that we present. And so out of metabolic considerations, people started to realize that actually the brain is only using a tiny amount of energy from its energy budget to process these evoked activities. And so that's how especially people like Marcus Reichel started to think about or investigate the intrinsic activity of the brain. And so it was first observed by looking at the task negative or deactivation patterns in conventional stimulation neuroimaging data that you actually could find consistent brain networks that were task negative, so that were kind of deactivated and in other words became active during resting periods. And so this is actually initially this was termed the default mode network, which some of you probably have heard of. Now, since then, the methodology has evolved, and now today we're able to identify multiple resting state networks, and we have also found that they are relevant for disease and disorder. And so some people say that there might even be the key to understand, let's say, the basis of consciousness, sorry. And so it's a very interesting field. Now, since we're in Vancouver, I tried to put in a Canadian slide here. And so if you like to go fishing for fMRI resting state networks, one way to do it is to pick a specific hook. And then you go fishing for the fish that goes with that hook. So that would actually correspond to the seed voxel correlation method, where you pick your seed voxel and then you do the correlation with the time courses of all the other voxels in your brain. You get a correlation map that you will threshold, and so you identify the network from which the seed voxel is actually the hub, or let's say part of that network. And so that works pretty well, as you can see here in this illustration. Here are each time you have a seed voxel that has been chosen, and you have a corresponding resting state network that's lighting up. Now the other method is to rent a boat with a big net, and you go fishing, and this net is made such that you can take all the fish together. And so this actually would correspond to methods such as blind source separation, independent component analysis, for example, which allow you to identify in one step several networks, and if you apply it to resting state, several resting state networks. So actually this has been a great market for the ICA methods people, the fact that people started to look into resting state. Now the research question that we want to answer today is to actually have a better insight in the electrophysiological correlates of these fMRI resting state networks. Because as you probably know, what we are measuring with fMRI is really a proxy for neural activity. So you have all these intermediate steps that link the initial neural activity to actually the bolt or blood oxygen level dependent signal that you measure with fMRI. And so this is actually a complex interplay to get from your neural activity to your bolt fMRI. Now, if we are measuring scalp EEG, we do have a smooth, we don't have direct access to the electrophysiology inside the brain, but we are actually closer from the nature of the signal to the neural activity in the sense that we are measuring electrical activity. And so we would like to see if we can find some clear correlates in EEG for the fMRI resting state networks. And as a second question, we hope to find some better insights in the cognitive relevance of these fMRI resting state networks. Because there is an ongoing debate in the community whether these resting state networks reflect intrinsic activity, which is there because these large-scale networks do exist in your brain, and so they need to be maintained to keep the machinery running, versus do they reflect really spontaneous behavior or, let's say, conscious mentation? So like really cognitive building blocks of what's your brain doing. Now, if you're thinking about EEG, you're probably thinking right away about EEG rhythms, because that's a standard way to analyze your EEG. And so today we are lucky that we can acquire EEG inside the MRI scanner. Of course, you get an EEG which is quite dirty, but today we have the methods available to clean the EEG. We can remove the gradient artifact, we can remove the ballistocardiogram artifact. I won't go into details for that, but it's possible to clean your EEG acquired inside the MR and to get a decent EEG that you can analyze as it was acquired outside. And so Lars and colleagues, in 2003, they did an EEG-informed fMRI analysis where they built a regressor out of the alpha band energy, which is around 10 Hertz. They actually convolved that signal with an hemodynamic response function, which is a simple model for the system response between the neural activity and your bolt fMRI signal. And so they found that there is a network that correlates with this alpha band informed regressor. And it's something known as the attention network. And in subsequent studies, they further refined this result, and they added into the equation the beta band that would also modulate actually this alpha band correlation with the attention network. Now there was another study in 2007 by Corbetta, Mantini and colleagues, where they did a more sophisticated methodology, and they first actually identified fMRI resting state networks, which you can see here, and then they looked for a signature for each of those fMRI resting state networks on how much energy is contributed in the different EEG bands to each of those fMRI resting state networks. And so what you can see here, so these are the signatures of the EEG with the each of the fMRI resting state networks. You can see that actually these signatures don't tell you very much in the sense that there would be a clear link, for example, between beta and a specific resting state network. So they all contribute basically to some extent to each of the networks. So it's hard to draw a conclusion out of this result. And so that's actually the starting point of our study, where instead of looking at the frequency content of an electrode from your EEG recordings or a set of electrodes or a weighted combination of electrodes, we are going to look at the topography of the EEG, which basically means that we will now fix a point in time and we will have a look at the spatial distribution of our potential as we measure it. We will actually do average referencing, so we are reference independent. And then we will look at how this topology evolves over time as we move our time point. And so what has been noticed 40 years ago already by Dietrich Lehmann from the University of Zurich is that if you look at spontaneous EEG, and so what you see here is actually a sequence of 12 seconds. So every step here is 45 milliseconds, and red and blue is showing the polarity. And so this is kind of the EEG seen from the top, from above the subject. And so what you immediately notice is that the topography is not like randomly changing at every time step. The polarity is changing a lot, but the topography itself is staying stable, typically for periods of about 100 milliseconds. And so Dietrich Lehmann called this metastable states, and he termed these as EEG microstates. So it's kind of an approach which is orthogonal to the typical temporal analysis of EEG. It's really a spatial topographic analysis of the EEG. Now, in the very beginning, actually, Dietrich Lehmann did this analysis by hand, because 40 years ago we didn't have all the sophisticated machinery to do it automated. And so he basically drew vectors between the peak of the positive and the negative potential. And so he noticed that this vector, which then, if you don't look at the direction of the vector, you're insensitive to polarity. And he noticed that the vector remains stable during, let's say, 100 milliseconds periods. And so this way he could segment manually the EEG into microstates. Now today we can do it automated and easier. So here you see a segment of EEG. And here you see, for example, the topography at this point in time, over here, over here. For example, if I look around this point in time, I see polarity is changing, but the topography remains stable. So what we do to do this in an automated way is we look at the signal of the global field power. So that's what you see over here, which is basically the variance, the spatial variance of your EEG over time. I mean, over space, but at every time point, right? So this is the variance over space. And now you take all the topographies from the peaks, so the local maxima of the global field power. And you throw those into a clustering algorithm. And so using, for example, cross-validation, you can then show that in a very reproducible way, you always find 4 topographies that dominate the EEG. And so those topographies, they look like this. It's like the usual suspects if you do this analysis to spontaneous EEG. And so once you have determined the centroids of your clusters, you can then go back to your EEG data and you look at each point in time, where do I correlate best with each of my templates, and then you can assign a label to do a microstate segmentation in time of your EEG. And you have basically reduced your EEG data in just a sequence of labels, which if you pick 4 microstates, it would just be a label between 1 and 4. Okay, so the fact that we only have 4 EEG microstates has been confirmed over and over again. And so the biggest study that has been performed was by Thomas Koenig in Bern, where he had a very large cohort, more than 500 subjects, actually aging from 6 to 67. And he could find over and over again these 4 microstates. There were slight variations, age-dependent, like in the average duration of certain microstates, but very consistently, he found always these 4 topographies again. And so we have some indications today that these EEG microstates, they do have a functional meaning. And so there are 2 strong points of evidence for that. The first one is that the pre-stimulus microstate in tasks such as visual perception, they do influence the behavior to that perceptual task. So there should be a functional meaning of those microstates. And secondly, some parameters of the microstates, such as the duration, is modified in some mental disorders. For example, in schizophrenia, there is one microstate which has clearly a shortened duration. So which also indicates that there might be a functional meaning behind it. So what we did is we applied this EEG microstate segmentation now to resting state fMRI, where we simultaneously acquired the EEG, we cleaned it. We had 8 subjects, 3 runs, every run was 5 minutes. The original EEG sampling, so this is 3 Tesla data, the original EEG was sampled at 5 kilohertz, and over the cleaning, we went down to 125 hertz in the end, low pass filtered at 40 hertz, which is, let's say, normal EEG broadband, if I may say so. And then so we looked for the clusters of every subject every run, and you can see that these topographies that we end up with are very similar to these 4 usual suspects as were found in the literature before. So if we average actually all those maps over the group, we really get typical topographies that were found before over and over again. So this shows it's possible to acquire the EEG inside the MR, clean it, and again do these EEG microstate analysis. Now then, to make the bridge from EEG to fMRI, we did the following. So what you see here is just a piece of the data after the EEG microstate segmentation of 4 seconds. And so you basically see 4 indicator functions which are stacked on top of each other, and each of them is indicating the presence of one of these EEG microstates. So for example, the green one is indicating when this one is present. Okay, so what you see here are 4 indicator functions. And now to make the bridge between the EEG and the fMRI, we do what everybody does. We take the canonical hemodynamic response function out of SPM, for example, which is a very huge temporal blur, right? So this is 20 seconds. This time to peak is like 6 seconds. So it's really a huge temporal blur compared to the dynamics that you observe in the EEG microstate segmentation signals. And we convolve each of these indicator functions with the HRF, and we get a function that's now, of course, slowly varying. So you see here now the result, but this time the time scale is 4 minutes, otherwise you wouldn't see anything. And so you see that this signal is slowly varying indeed. And at first glance you would think, okay, this is worthless because there is no more information left that is really meaningful. But if you just look a little bit closer to these convolved signals, you can see, for example, that there is an anti-correlation between the green one and the blue one, which is kind of strange. So we thought, okay, let's go on and let's try to put them in a general linear model. So we use those 4 functions now as 4 regressors, together with a 5th regressor, which is just a constant, just the baseline signal. And we do the standard GLM analysis of our fMRI data that we acquired at the same time. And so if you do that, you find significant correlation with 4 networks. So it seems that the regressor that corresponds to this EEG microstate significantly correlate, and it's actually a negative correlation, which is a bit puzzling, but I come back to that later. There is a negative correlation with a map that you can identify as the auditory network. This one correlates, again negatively, with the visual network. This one over here correlates basically with regions like ACC and can be identified or termed like a self-referential network, if you like also executive control, depends in which literature you look, but let's say a more high-level network. And then the 4th one correlates with an attention network. Now this is very nice, but are they really the fMRI resting state networks? So to confirm that, we did an ICA, a group ICA, on the fMRI only, so no EEG this time. And so we then actually did a statistical pairing to see whether we can pair each of those maps with one of the maps that come out of the ICA analysis. And so we could find that each time there is one pair that is really statistically significant, and so you can see here each time the corresponding ICA fMRI only resting state network can be identified with the GLM maps that we got from the EEG informed analysis. So this is our first result, where we were very happy about, but it actually raised more questions than we got answers, because we were really puzzled by the fact that starting from these very fast dynamics from the EEG, convolving it with the stupid HRF, you get a significant map doing the GLM analysis. I mean, how is it possible that there is information that goes between those two timescales so different? And so this is how the hypothesis came that there must be actually something in the initial signal in the EEG microstate sequences that is perhaps kind of a fractal organization. Because if that would be true, then if you do smooth the signal, you would actually see the same type of signal at different timescales appearing. Now, if you're talking about fractals, you probably think about Mandelbrot fractals. So he fortunately recently passed away, but he contributed tremendously to the field of fractals, and probably you know the Mandelbrot set, which is a mathematical formula that you can evaluate at any scale. It always looks kind of the same, and so it is really self-similar at infinite scales. Now, it's not this type of fractals that we're talking about. We're actually talking not about deterministic, but about statistical fractals. And a statistical fractal is a signal or a process that generates signals that if you look at the statistical measures of that signal at different timescales, you cannot distinguish them. So they are not exactly the same, but they are statistically the same. Or they just scale with a very simple parameter. And so these statistical fractals have been applied a lot as well. They have been applied to stock market index, of course. People always try to make money. I don't think it was so successful, actually, given the current status of the stock market. But it has also been applied with more success to many physical and biological processes. For example, heart rhythm has been extensively analyzed using a statistical fractal model. Now, to analyze the fractal properties of our EEG microstates, we will follow a methodology that has been applied to the analysis, the fractal analysis of DNA sequences. And now, in DNA, you have the 4 bases, and we have the 4 microstates. So somehow, maybe our EEG microstates are like the DNA basis of thoughts or cognition, maybe. Anyway, so we do have the 4 microstates, and so the first thing we will do is we need actually to choose a partitioning. So for example, we take partition 1, which is microstate 1 and 2, partition 2, which is microstate 3 and 4. So you do bipartitioning of your microstates. And then you build a step function, which will walk up when you're in partition 1, and which will walk down when you're in partition 2. Okay? And now you just accumulate this step function over time, and you get what is called a random walk embedding. And this is the signal that you will submit to fractal analysis. Right? So you need to, from your labeling sequence, you need to transfer this into a random walk embedding. And then you can analyze it to see whether it has fractal properties. And so this is just to show you how it looks like for real data. So here you have a 4-minute sequence, and I did some zooming into 45 seconds, 24 seconds. And you can see that just by eyeballing, there seems to be indeed there could be realization of the same process, although we are looking at different time scales. But to be sure, you need, of course, to analyze it with the mathematical method. So to put this a bit more in equations, so with a self-similar process, as said, we mean that we cannot statistically distinguish the signal from one scale to another up to a scaling factor. And the scaling factor, so if you dilate your time scale with the dilation factor of A, you can allow for a scaling factor, which is a to the power h, and h is the famous Hurst exponent. And then you have a true self-similar signal, where there's only one parameter that actually characterizes the whole signal at any scale, in a statistical sense. Now, such a signal, of course, it has no characteristic scale anymore. There's one single parameter. It's non-stationary. It has long-range dependencies if h is bigger than 0.5. And we can characterize it typically by a variogram, which is the expectation of basically a finite difference of your statistical process, where the step I use in my finite difference is A. And so what you see is that this expectation of this finite difference put to absolute value a power exponent q is basically just a simple function of my step of my finite difference. Okay, and this is well defined. I mean, this is again, here you can compute an expectation, because this finite differencing is taking away actually the singularity of your non-stationary process.
What is the first signal? Look at joint marginal, so any order, the probability log is the same for every day?
Yes, yeah. Or you compute moments, or you try to analyze it. Yes, yes.
And then the variogram is just one way of looking at this, and if that's true at the top, then this will turn out to be true for the variable.
Yes, indeed. So an easy process to think about fractional Brownian motion. And so then actually the increments, they are a Gaussian process, a simple Gaussian process. Now the right tool to analyze this type of signals is to use the wavelet transform. Because by nature, the wavelet transform uses a mother wavelet that you will dilate and shift to analyze your signal. And so let's say this mother wavelet, or the wavelet transform, has this scale invariance built in as a design principle of the representation. And so if you would take your signal now and you do a wavelet analysis, and what I've drawn here in the background is actually a continuous wavelet transform. So what you would see at any point is a wavelet coefficient at scale A, position k, which is the imprint, if you like, of your process with the wavelet dilated and shifted to the right position. And now you can show that these wavelet coefficients at a given scale, they become stationary again. Because what the wavelet actually will do, it will do a multi-scale implementation of your finite difference. So it will actually do this type of difference, but in a more elegant way and at different scales. So it turns your process into a stationary one. And the self-similarity property now translates into a relationship between the statistical properties of your wavelet coefficients at different scales. And so you can analyze those properties now in a scale-dependent way. And actually, the long-range dependencies turn into short-range dependencies. Now, although I like to show you the continuous wavelet transform, because I think it's nicer to look at, and it conveys you more like the very nice propagation, for example, of singularities through scale. In reality, we use the discrete wavelet transform because it's more efficient, and it's a basis. It's a one-to-one mapping between your input signal and your wavelet coefficients. Okay, so let me just show you once more the very nice continuous wavelet picture and try to tell you what we're after. So this is for a real signal where we took the random walk embedding signal of 4 minutes, and here you see, let's say, the wavelet spectrum, if you like. So time is over here in this direction, and now if you go down, we actually go deeper in scale, which means that we go to lower frequencies, if you like to see this as a frequency. And so the typical dynamics of EEG microstates, which are about 100 milliseconds, they would be around here. And the typical dynamics of fMRI, which I assume around 10 seconds, they would be around here. And so the question we're trying to answer is, would there be a scaling relation between those two timescales at least. And that would then explain the relationship that we find using our previous GLM analysis. Now, to do so, you need to compute actually what is called the structure function. Now, the structure function is not very complicated, although it might look like. So what you need to compute is at a given scale j, and for a chosen power exponent q, but let's think for q equal to 2 now. So we're looking at energies, in fact. And then what you will do is, so imagine q is 2, you will actually compute the energy of the wavelets coefficients at the given scale, right? And so if you do that, and you plot those, and you plot them here as a function of scale. Now scales are dyadic scales, so this is actually a logarithmic axis, if you like. And here the energy is plotted again on a logarithmic axis. So what you can see is that we have a clear power law behavior between 256 milliseconds and 60 seconds, which are kind of the equivalent frequencies at the respective wavelet subbands. And so this is now this region where we do have this power law behavior, we will use it as our fitting region. So we will say from now on we will fit all the structure functions for other power exponents q, we will fit them in that fitting region. And so I think it makes sense in the way that if you have typical microstate dynamics, where let's say the microstate can go up to 100 milliseconds, to be able to see something happening on a dynamic point of view, you need to have about the view, the wavelet needs to see about the view of 200 milliseconds. So it makes sense that you need to go up to that, or let's say starting from that length, you do see something happening in the dynamics of the microstate. And of course, here we're limited by the limited acquisition, the duration of our acquisition. Because at some point, we don't have enough data anymore to have a reliable estimator of those structure functions. Okay, so now this result alone would actually allow us to say already that we do have a self-similar signal, but it would only be in a very weak sense. If you like, this is actually equivalent of taking a signal, doing the power spectrum density, and looking at a power law behavior. And which actually is done a lot in the literature, but it's only a very weak indication of self-similarity. Because to have a strong indication of self-similarity, you need to do this now over and over again for different power exponents q. And so if you do that, and you plot them, you actually, so you do that for each possible power exponent q, and each time you determine the slope of your power law behavior inside the fitting region, and you put those now on what is called the scaling spectrum, put those on a plot. So that means that for each point here, and so q ranges from -5 to 5, for each point here, you have fitted you have fitted the slope and you have reported it over here. And so now, if again all those points they lie on a straight line, you have now a strong indication of monofractal behavior. Because this line should really be like q times h, where h is the h vector. And so as you can see, this is for real data. So you see that they do lie on a straight line. And actually, the dotted line over here corresponds to h equal to 0.5, which would be the behavior or the slope you expect to find for white noise, which is actually also a self-similar signal. So we do have long-range dependencies, and we do have monofractal behavior. Okay, so now you can do this for the h subjects that we have, and the Hurst exponent that we find is indicated here in light blue, and so it's typically like between let's say around 0.6. And now we did two verifications. So first of all, we took the same microstate sequences and we shuffled all the labels, like a permutation of the labels, but keeping the timing. And then we redid the fractal analysis. And you see that the Hurst exponent is basically unchanged. There is statistically no difference between the Hurst exponent you find for shuffled labels or for the original sequence. And as a second experiment, we kept the microstate labeling, but we put them all to equal to average duration. So we destroyed, if you like, the timing of the microstates, but keeping the right labels. And then you really go to white noise properties. So then all of a sudden, the Hurst exponent fits 2.5. Which basically means that this fractal organization is really in the timing and not at all in the memory of the labels, right? Because if you keep the labels but you destroy the timing, it's absolutely looking like white noise. And you probably have wondered, what is the influence of the choice of the bipartition? Because this is a choice we need to make. We need to bipartition into 2 partitions, and you can do this in 3 possible ways if you have 4 labels. And so here you see the results for the other bipartitions. So in the case of our healthy subjects, there is absolutely no difference dependent on the bipartitioning choice. Okay, so what does it mean? So actually, if you look in the literature, there have been many, many measures of scale freeness in brain signals. So in time, these have been seen in intracranial EEG, in normal EEG, like electrode by electrode, in fMRI, also now recently in synchronization between MEG and fMRI, and so on and so on. So usually, unfortunately, these scale-free measures have been determined only using the weak property of self-similarity, which means like power spectrum density and then looking at the power law in the Fourier domain. Now there has been also power law behavior or scale-free measures in space. So you probably know about the work of people like Bullmore and Sporns, where they have actually these scale-free small world networks that seems to pop up and so on. And so, but as said, these are usually not using strong measures of fractality. And so I think here, what is kind of striking is that this temporal organization of the EEG microstates really has a monofractal behavior. And I think it's rather strange to see that with a physiological signal. Because actually, to maybe say something more about that, so we had 8 subjects, and we had 3 runs per subject, and there were 2 runs. So there were 2 runs where the Hurst was completely off, like 2.8, something like that. And so when we then partitioned the data into 2 halves, there was one half which was again okay, 0.6, the other half which was off. And so this way we further partitioned the data, and we could actually localize an artifact that was not well dealt with by the BCG artifact removal. So it's what I want to say is that it's really a very sensitive measure, and if there is really something wrong in the data, it will have a consequence although it's just a single moment in 4 minutes. So it's actually a good artifact detector. And so it implies that there is a non-stationary behavior in the data, and we do have long-range correlations, which has been confirmed before, but it's yet another confirmation. And it does explain this link that we find between the EEG microstates and the fMRI bolt oscillation. Now, I'd like to mention some recent work by the colleagues from Neurospin, by Philippe Chouchou and Andreas Kleinschmidt, where they looked at fMRI resting state networks, so without EEG, and they did very fast acquisitions for a very long duration using echovolumetric imaging. And so they start from the fMRI itself, and then they did actually the same type of wavelet fractal analysis, and they could find multifractal properties of these resting state bolt oscillations. So which is, I think, kind of interesting, because if we found between the EEG and the fMRI a monofractal relationship, and they now start from fMRI, which has been kind of influenced by the hemodynamic system already, so it seems that this monofractal nature has been turned into a multifractal nature due to the influences of the hemodynamic system. So I think this is an interesting connection. Now we are getting towards the end of the talk, so I can get a little bit more philosophical. So what does it mean, this scale-free or monofractal properties? And so there it starts to be more philosophical, as I said. So actually, many people are convinced that fractal signatures, they are actually the sign of the brain being a critical system, where, or a self-organized critical system. And so where you could imagine a subcritical system as being kind of a deterministic system, like a Swiss watch, right? And then you wouldn't really actually need a complicated brain. You could do with a very simple brain as well. So it's not subcritical. A supercritical system would be a chaotic system, which of course you wouldn't need the brain. And a critical system would be just right. So it would actually allow you to adapt to the complex nature of the world, which basically the brain is designed to operate in the world, which is changing and complex as well. So the critical system has just the right properties to interact with this complex world, to actually remain a little bit chaotic, so you have not everything is foreseen, but at the same time being deterministic enough to survive. And so this self-organized criticality has been strongly influenced by people from theoretical physics that actually built also physical models for self-organized critical systems, such as the sandpile model and so on. And so this seems to be a universal organizing principle that's often emerging into complex systems in nature. And so you can find them actually in many, many examples there, like social interaction and so on. You do have critical organization. And one way to see this for the brain is that it's the brain's way to meet the challenges of the moment, right? So being critical means it's ready to adapt and reorganize fast and efficiently, depending on the demands from the inside and the outside world. Okay, so I like to mention a little bit what we are trying to take this further now, or how we're trying to take this further. So we want to get rid of this bipartitioning, because I think it's not a very natural way of going from the EEG microstates to the random walk embedding. And we would like to go into a multidimensional random walk embedding, which provides actually a one-to-one mapping between your random walk and the EEG microstate sequence. And so to do so, we will actually use equiangular frames, which allow you to have a very nice multi-dimensional representation of a microstate sequence, which is a one-to-one mapping. And I think there is still work to be done, which is actually how to link this finding with studies more in computational neuroscience, and in particular about nonlinear dynamical systems, to understand what it really means for the brain as a kind of a generative model, right? Because the signature that we find, it doesn't tell us how the brain exactly does it. It's a manifestation that we observe, but it doesn't tell us the brain reaches this goal using this or this architecture. So I think there is still a lot of work to be done there. Okay, so to conclude, here you can see actually a random walk embedding of 3 runs concatenated. And so I will zoom in and out, so it will zoom in until 20 seconds. And now, if you just randomly close your eyes, like for 1-2 seconds, you open them again, and you try to guess what is the time scale without looking at the bottom left of the screen. You will see that it's actually quite hard to know where you are as a characteristic length in time, I think. At least for me, it's hard. And so then to conclude, I like to just make a little analog with an article I saw by accident in Nature Communications, which was about diffusion of liquid phases in microgravity. So this seems to be a process that if you do this physical experiment on Earth, there is like nothing special that happens. But if you do this in space, in microgravity, you do have also these fractal properties that do emerge. And so somehow I like to see this, that nature has created the brain in such a way that it has provided like a little sandbox where where our thoughts can play, and they can play in such a way that everything is according to this wonderful monofractal structure. So with that, I'd like to conclude. Thank you very much. So there is no frequency filtering. So we go down to, let's say, the broadband EEG up to 40 Hertz. So there is no separation into bands. And then we determine the topographies by clustering of this signal that we get from the maps of the peaks of the global field power. So some people have extended kind of a mixed view like microstates, which are subband dependent, right? It's like microstates in the alpha band, the beta band, but here we didn't do that. So we took like the original microstate idea, which is you only look at space.
Also, I was intrigued that you're saying this apparent fractal nature, in Latin American it's called APF, or APR fractal, but the base fractal curve is strictly temporal?
Yes, yeah, this is a purely temporal analysis. And so we reached to like 20 seconds, but I think given the work using the multifractal analysis of the very long duration fMRI signals, I think it might actually reach even further than 20 seconds. I mean, we should do acquisitions too, which reach up to, let's say, 20 minutes to confirm this as well. But I think since this was like 20 minutes acquisitions in fMRI, and they started from a time scale which is about the time scale where we end, and they could find multifractals up to like multiple minutes. So it's really amazing that the brain has this temporal embedding over such scales. No, I mean we did a couple of experiments to invalidate any effects of filtering, and we actually even mapped back, okay, some like the gradient artifact we need to get rid of, but that's actually quite an easy correction. But we even looked at the very raw part of the EEG by taking our typical topographies and mapping them back to the EEG at a very high temporal sampling rate still. And so even there we could find exactly the same monofractal structure. And also with EEG outside the MRI, we do find the same. So we had another control experiment for that.
Take my question. Microstate 3 was essentially maybe a combination of microstates 1 and 2.
Not really. So microstate 3 is the executive control. You in time, you mean?
They looked as though you could construct 3.
So of the regressors in time. So they have correlation. They are surely not orthogonal, but they. I mean, you can still do. I mean, we put them together in a GLM. No. So they are not orthogonal in space. The original microstate sequence in time. So without convolving with the HRF, it's orthogonal because the way we represent them here, it's an indicator function. So if one is on, all the others are off. So in time they are orthogonal. But after convolving with the HRF, the orthogonality is gone. And so there is collinearity, but not. I mean, we can still estimate them with the GLM all together. So it's not one by one; it's all together.
Just the future of sort of robust brain-computer interfaces, it seems to be going in the direction of tracking the cognitive process through tracking microstates. And I'm curious if you think there is an anatomical analog, like something's underneath them, like the basal ganglia is running the switching mechanism, or is it just an emergent property of the brain?
It's a very hard question because each of these topographies is really not something I would be daring to do source localization on those. It's a very widespread potential. So Yeah, I mean, I would even be very careful with the link between the anatomical networks that we found, which is a correlational link, for each of the microstates, and so these fMRI localizations, because there is an intriguing thing like, why do we have 3 out of 4 which do negatively correlate? I actually have no answer for that, and there is 1 out of 4 which is positive. And you could see the 3 that are negative as more sensory processes, right? Auditory, visual, attention. And then the one that is positive is more like a control process. Yes. It's still intriguing, I think.
So I think I'm going to ask the same question, but maybe it's a complementary way. So I don't want to ask about your indicator functions. I want to ask about the templates on the sphere, right? So you definitely you led us down a path in which you linked them to the resting state networks, right? And you know this literature better than I, but you know what's coming out of the Buckner, MGH people, where they're sort of looking at these hubs, and they're arguing that these resting state networks are somehow linked to these hubs, related to these hubs. Maybe related to heteromodal cortex, related to areas that are just huge gateways, and right, and we don't know. I mean, we don't yet know about what the resting state networks really are, and that. So it's in that vein. I just want to ask you. So, is the color on the spectrum, the template on the templates on the sphere, are they just the result of taking all the EEG, integrating it over the volume, looking at it on the boundary of the sphere, and the one that's correlated, I'm going to try to make a huge leap here just because I want to think about this. The one that's correlated to one of the resting states, which is related to the hub of, auditory, is that the hub is near, it's somehow where its position is, it's resulting in the overall average field looking like that. Is that how I should think about it? Before I go to all your other stuff, is that how you think about it? That if there's this hub of neurons related to the resting state network, and I end up with this color pattern, which is positives and negatives, that's the result of integrating over the whole volume, subject to all the material properties and all the shielding and all that stuff. Is that what gives the color?
I would not dare to interpret it directly like that. No. And so we don't find also the default mode network, which is the one which is mainly studied by Buckner and many other people. So I don't know where it's gone. It's
self-referential, but you can manipulate it.
Yeah, but it's
Self-referential state.
yes, but the default mode network itself, it's not part of the region.
No,
Yeah,
but something that's related to it is certainly
probably. Yes.
But you're not thinking of it that way. So because that's fine. If you're not, then it just means
No,
okay. I can't try to simplify the world with that.
I would not dare to make that direct link.
Then the other thing I was going to ask you is, for self-similarity, if I take the operation x of t minus a, we know that e to the I omega t, things like e to the I omega t, are eigenfunctions of the shift operator, right? The eigenfunctions of the divide by scale operator are t to the power. So like t to the I omega a would be an eigenfunction for x of t over a, right? So that suggests that if you take the time axis and you just take the log of it, there's a very nice decomposition back to sines and cosines. But you would work with expansions, not the usual Fourier thing, but you would sort of log, you'd log your data on the time axis, and then you'd work in expansions of sine of log t, cosine of log t and its frequencies. Do people who do this kind of temporal self-similarity, do that?
They do that to generate synthetic signals that do have these fractal properties.
Yeah, but
it would be reference point dependent. So you get what they call a cusp signal, which has this logarithmic compression.
Use the wavelengths, it would be
change the time axis because if you look at this logarithmic time axis, it's in that axis this is a very natural decomposition.
Yes.
It's simple. It could be a narrow band, representation, even though when you then change the time axis again by exponentiating, then you end up with something that has frequencies and correlation.
Yeah. So I've seen it for the synthesis, but I don't know a method that uses it for the analysis side. But for the synthesis, yes. It's a trick that's used.
So you mentioned Michael Trace there and this discovered that you do is nonlinear dynamic simulation.
So that's an open. It's not what we do.
Yeah. They found evidence of this bimodal, spontaneously generated bimodal structure. But that's not exactly what the intelligence is there.
It's not the same thing.
And that comes out purely from laying down the white matter tracks with Wilson Allen oscillators in each head, and then putting in a length dependence based on the velocity. And then the system just organizes itself into these sort of bimodal criticals type oscillation. So this is something that will be answered soon, I would imagine.
So I think they didn't look at the scale-free properties yet, from what I understood from their work. But it looks like a state switching system, if you like. So there is a similarity there.
Sorry, I'll pass it to you in just a second. My personal choice of wavelet is the Dobschi's D4, and that choice was motivated by an old saying among people who work with wavelets that the more your wavelet looks like your data, the better it's going to work for you.
Here you can choose actually any wavelet you like. So Dobschi 4 is fine. I would say, I mean, in this case, it needs to have at least one vanishing moment. So it needs to do this finite differencing operator. Otherwise, you don't stationarize your process. You could go a little bit higher than 1, because that will remove like drifts in your signal, like slow, let's say local polynomial drifts. If you have enough vanishing moments, you will also kill those polynomials. So that could be a reason to go to a bit more higher. So I think here we took Dobschi 4, I think. That's probably, but we tried several ones. It doesn't change the result. Yeah.
So if you take the default mode, and if you look at the distribution of the microstate, if you take the temporal aspect of the default mode, and then look at what is the distribution of the microstate during, where there's the default mode is on somehow. Do you see uniform distribution on microstate, or
we didn't look at that actually.
That'd be fun.
So we played a little bit around with a similar idea, and it seems to be that there might be some correlation with the default mode, but I say that as a very, I wouldn't put my hand in fire, but it seems to be that the default mode activity is basically correlated with kind of the sum of all microstates together. But it seems to be...
Which is a bit bizarre, because the sum of more microstates, I mean, if the microstates are...
Sorry, so the onsets of all the microstates.
Oh, the onsets, okay. Yeah, that was another question I had.
So
actually.
maybe it's the switching process.
We could also look at the transition. I mean, you may have different distribution of transitions between the states.
Yes, but then if the process is really non-stationary, it doesn't really make a lot of sense to build a transition matrix. And at least this fractal property is completely...
the distribution of the transition could be also related to some aspect of the default mode temporarily.
Ah, okay. Okay, yeah, maybe.
I have a question which is slightly off of the brain topic, but you mentioned that you need to remove the BCG artifact from the EEG signal. But it's striking to see how do you get a BCG while the person is lying down as an artifact in the EEG signal?
So it's due to movement of the respiration. I mean, you're in this huge magnetic field. Your electrodes are slightly moving, and that is generating a very nasty artifact, which in some subjects is actually easy to identify with temporal ICA on the EEG. You get a kind of characteristic spatial map that you can then subtract out of the data. But in some other subjects, it's really hard to get rid of. And because it's not like purely periodic and it's slightly changing over time. But it can be done. It's
Okay.
Cool.
it's manual.
Philosophical discussion, maybe this could go on afterwards. You did one thing, you did lots of wonderful things, but you did one thing I objected to strongly, and that was call all the things ICA produced networks.
Okay.
I
I'm
mean,
sorry.
they're simply a set of non-orthogonal representations of some subspace, linear subspace. And maybe some of them are actually identifiable things that we can coherently manipulate in the brain. But I think the field's got a bit...
It's a bunch of components. That's bit.
Yeah, I know. It's easy to call them networks. The trouble is all this baggage comes along
That's
with
true.
it. And
Yeah.
you know, entire literatures are now being driven by the number of ICA networks that are generated.
Yeah, as I've said, it's a big market for IC now.
Yes, that was right.
If there are no other questions, I'd like to thank the speaker once again.
Thank you.
Also, another great round of applause for all the speakers for wonderful talks throughout the day.
Thank you.